All right, welcome to video 1.2. This is the second half of chapter 1. We're going to talk about some key concepts in measurement science that are relevant to chemistry, specifically accuracy, precision, uncertainty, and then ultimately this idea of significant figures, which is going to carry through the course pretty importantly. So any measurement that you try to make is your attempt at approximating a true value, some natural value in the physical world that you designed some tool to try to approximate it. And so an example could be you trying to approximate or measure the rate at which your vehicle is moving using this thing called a speedometer. And so that's what we're showing in this picture up here. So in this picture, we can see that we're moving probably about 55 miles per hour. But when we think about the language of science, we have to think about, well, how close is this measurement to a true value? One, if I did this measurement 10 times, am I going to get the same answer every time? Is it consistent? And ultimately, how many digits do I know, right? In this example, do I know this value just simply as 55? Or do I know this value as 55.1 or 55.12? Right? All of these are relevant as a scientist because you don't want to over-report your confidence in the measured value, and you don't want to under-report your confidence in a value. Often the confidence you have, the more digits you want to include in your measurement, that scales with the expense of the experiment. So if you want to know this to great detail, 55.15793, you're probably going to have a more expensive tool than the simple speedometer that's equipped in your vehicle. Okay, so this leads us to this idea that every measurement you make has some sort of uncertainty associated with it. So uncertainty is really another word for error. And so there's really two different general types of error in chemical measurements. We have what's called systematic error, and we have random error. So systematic error in the example of your speedometer here could be an example where when you bought your vehicle, that speedometer was miscalibrated at the factory, which means that you were reading a value of 55 miles per hour, but maybe it was miscalibrated and you were actually going 65 miles per hour. That means that your value is systematically lower than what the true value is. It's out of your control, but once you identify this, and maybe that's because you get pulled over speeding, once you identify it, it's controllable. And that's the benefit of systematic error. So systematic error is once identifiable, it's something that you can control, which means maybe you take your vehicle back to the factory and you recalibrate your analysis. So when you're doing a chemical measurement, you can imagine there's a whole bunch of different ways that systematic error can manifest. It could mean that you're using a piece of glassware improperly because you never learned how to use it. And so you think you're reading it correctly, but you're reading it incorrectly every single time you use it. The same can be true for any electronic measurement device that you're using it if you're just using it improperly or it's miscalibrated. That's a type of systematic error. The other type of error or uncertainty that manifests in chemical measurements is the random type, and as the name implies, this type of error is often or almost always uncontrollable and often unidentifiable because of it. So the example of random error would be maybe you're measuring the velocity of your vehicle using your speedometer, and you try to do this in a controlled way. So maybe you get it up to speed and you measure your velocity 10 different times, or maybe you do it 100 different times. And so if we were to sort of plot those measurements on a number scale, and maybe your average is right in the middle and it comes out to 55 miles per hour, what you'd see is that if you did this n equals 100 times, you'd end up with numbers all along this scale, and you'd end up with a nice looking bell curve that looked like this. We call this the normal distribution. And the reason why, if you do your measurement lots of different times and you don't get the exact same answer every single time, is because that thing, that quantity that you want to measure, which is speed in this case of your vehicle, there's a whole bunch of other smaller variables that contribute to that speed that you don't have control over. Those could be, say, the wind velocity or the wind direction, both of which could impact the measurement of your speed. It could be the friction of the road, the type of road surface, whether it's wet, whether it's dry, the humidity in the air. You can imagine there's a lot of different variables that impact the speed of your vehicle. Even though you're trying to do the exact same measurement every single time, it deviates slightly. You can see that most of your measurements cluster around this 55 mile per hour, but there's still some measurements that are off in these tails. This is a random error, and we can't control that. So when we're thinking about these original questions that I brought up at the beginning, we're often thinking about them within the context of these two different types of errors. So how close is the measurement to the true value is often another way to ask yourself, is there any systematic error present in the measurement? Let's scroll down here and use another analogy here to look at these questions. So we're going to use the bullseye analogy, which is the most common way to think about these two concepts called accuracy and precision. And accuracy and precision are really two metrics or two words that we use to represent systematic and random error. And so systematic error is often equated to the accuracy of your measurement, and the precision of your measurement is often related to the random error associated with it. So let's look at this first bullseye here in example A. So let's pretend that the true value of the measurement that you're trying to make is, metaphorically the center of the bullseye. And so you're conducting three different measurements here, right? N equals 3 because you've got three different darts. You throw this 3 times, and in scenario A, what you see is all 3 darts that you show are pretty far away from the true value, right? So what type of error would that reflect? Well, we said before that systematic error is something that's controllable, but it's systematically wrong, meaning the value you see or measure is consistent but different from the true value. In this case, that's exactly what we see. We see your 3 measurements actually cluster together pretty well, but they're all 3 pretty far from the true value, the average value here in the center. So we would say that this is inaccurate because you are pretty far, all 3 of your measurements are pretty far from the center or the true value, which means you have some systematic error. So if you have an inaccurate measurement, it means you have some systematic error present. But what can we say about the consistency of these measurements? Well, we can say that you threw 3 darts and you were pretty darn consistent at each point, which means that the random error that you see is actually pretty low. The uncontrollable part is pretty low. And so we would say that this type of measurement is precise but inaccurate. So precise means small random error. You're really consistent, but your 3 values were pretty far away from the true value. Okay, so let's jump over here to example B. So example B, again, n equals 3. It's the same 3 darts. The true value is right in the center. You threw all 3 darts. Not only did you get close to the true value, you got close to the true value for all 3 darts. So in this example, that means you are both accurate and precise. So accurate means that there is no presence of systematic error because your measurement was very close to the true value, and the precision meant that you threw 3 darts that were all very close to each other, which meant that the random error associated with your measurements was also very low. So this is as good as it gets, B. So if we look at the sort of third example here, what do we see? Well, again, true values in the center. This is the thing you want to measure. You throw 3 darts again, and in this case, all 3 darts are pretty far away from the true value, and they're far away from each other, which means that this is an inaccurate measurement, and it's an imprecise measurement, meaning you have both systematic controllable error and random error in the measurement that you're conducting at this point. Okay, so let's pretend that we have some real measurement values. So I have these written over here on the right side of the screen for the velocity of your vehicle. So let's pretend we know the true value somehow as 52.5, and let's pretend that you made your 3 measurements of your velocity at 55.3, 56.2, and 55.9. So how do we use these values in this true value to assess whether or not our measurements are accurate and or precise? Or in other words, how do we evaluate whether or not there's systematic or random error in these 3 measurements? Well, there's several different ways to compute this, but ultimately what we want to do is evaluate what is the average, drag that, what is the average of our, let's say, average, and what is the standard deviation? I'm going to write that as standard deviation. So the average is the mean, so it's the centroid of these 3 values, and the standard deviation is how far these values are from each other, or in other words, the consistency. So the average, if we take the average value and compare it to the true value, that's going to tell us how accurate we were, or whether or not there's systematic error. And standard deviation is going to tell us how wide that bell curve was of our measurements. If it's really, really wide, then that means we're not very consistent in our measurements. One comes up here, one comes up here, one comes up way over here. But if we have a really tight distribution of measurements, maybe our bell curve looks more like this, then that's a really precise measurement, which means we have very low random error. So you can compute this on your calculator, but I'd prefer you do this in Microsoft Excel. You'll do this in Lab 0. So I just popped in our 3 numbers here, 55.3, 56.2, and 55.9. I can compute the average by saying equals and then typing the word average and then selecting the 3 values that I want to average and press enter. I can do the same thing for standard deviation, but my formula now is STDEV, and now I'll put a parenthesis and I'll select just those 3 input values, and there we go. So we've got a value of 55.8 and we'll say 46 for our standard deviation. So let's write those down. So let's go down here, 55.8 miles per hour and 0. Let's say 46 miles per hour. Okay, so I said before that what we want to do is compare the true value of our measurement to our average. That'll be an assessment of the accuracy of those measurements. And then we want to measure or look at the standard deviation, the size of that, to evaluate our precision. So accuracy, if the true value is 52.5, but we actually are measuring 55.8, I'd say that's a pretty inaccurate measurement. And that points to the fact that all 3 of my measurements were higher than the true value. There's probably some amount of systematic error associated with it. Okay, and then with our standard deviation, we're only looking at 1 standard deviation here of 3 values, so this might not be the best data set, but it'll give you a sense. So that measurement, we measured 3 values and the standard deviation was less than 1/2 mile per hour. And so our distribution was actually quite tight, like this blue distribution here. So I'd say this is more similar to case A over here, where we had an inaccurate set of 3 measurements with systematic error, but those 3 measurements were actually pretty comparable to each other, so we'd say that this was precise. In other words, we would have some level of systematic error, but pretty minimum random error in this type of measurement. And so that's a really quick way, with using only 2 basic metrics here, random error and systematic error, to look at your numbers and get a sense for, well, how well do I know these? Am I accurate and am I precise? And it's really important to recognize that the word accuracy and the word precision are not interchangeable to each other. They're often used that way colloquially, but they distinctly mean 2 different things in the world of chemistry and physics. Okay, so that brings us to the third question that I'd mentioned previously, which is how many digits can we actually report with confidence? And that's directly correlated with the accuracy and precision of the specific measurement that you're conducting. And we call that the number of significant digits or significant figures in the measurement. And so what I have here are 2 different devices that could be used to measure the mass of an object. The one on the left is called a top loader balance or top loading balance. And you can see that this could measure in units of grams, and it gives us 3 digits here, out to the 100th place of grams. Whereas this tool on the right is what's considered an analytical balance, and you can see the number of digits it reports. It's a little hard to see here, but it's about 5 individual digits. Can report out to 0.0001 grams. And so these 2 objects, or these 2 different instruments, can report different numbers of digits or figures. And the best practice as a scientist is you never report any more digits than you confidently measured with the tool you chose. So if you chose the top loading balance, you could never have any more than 3 digits in your final answer. If you chose the analytical balance, you could never exceed 5 digits in your final answer. And you often don't want to underreport this. If you went to the extent of using this expensive analytical balance with 5 digits, then you better report your value with all of those digits. This analytical balance is on the order of $5,000 to $10,000. Top loader balance is usually a couple $100 in that case. And so, for example, maybe this top loader balance gave us for a sample 1.23 grams, but for the exact same sample, we brought it and we put it over on the analytical balance. Maybe it gave us 1.234 grams. Right? These are the 2 same objects that were measured, but now here we can only report 3 digits. We would say this has 3 sig figs. Over here, though, we would report this as 1, 2, 3, 4, 5 sig figs. And that's simply based on the limitation of the tool that you employed for your measurement. So there's a series of rules that we need to take into consideration when we're talking about significant figures. So if a value is reported already and you are asked to evaluate how many of those digits are significant, you can go through this list to assign what's significant and what's not. So the first example here is that all non-zero digits count as significant. So there's a couple examples here. So if you have a value that's 24, pretty obviously there are 2 significant digits in this value. If you have a value of 3.56, then there's 3 corresponding significant figures in this. So these are all non-zero values. For the second criterion here, leading zeros, those don't count. So those are zeros in front of any digits. So in that case, here, in the example of 0.0025, these leading zeros, they're essentially just placeholders. The actual digits that are significant correspond to the 2 and the 5. Where in space, how large this number is, that's not significant to the actual measurement. These are the quantities that were actually measured, which gives us only 2 significant figures. Captive zeros, those that are between non-zero numbers, those do count. So in this case, the 0 is sandwiched in between the 5 and the 2, so we would count all 4 of these digits, and we'd have 4 here. The same is true in the example of 1.008. We would have 4 significant digits. Okay, so the last number, or the last criterion here for the sig fig rules, is that trailing zeros only count if the number contains a decimal. So, for example here, if we have a value of 100, there's no decimal here. This is actually a really ambiguous way to write this number, so it's unclear how many of these are significant. So if it's written this way with no decimals, all we can say with confidence is that first digit, the 1, that's significant. These zeros that are trailing, we don't actually know if those are zeros or if they're rounded. Okay, so 1 sig fig for those trailing. In this case, though, we have a trailing 0, but it trails after the decimal, and that's the key here. So 2306.0, we would count all of these digits, these 4, including the trailing 0 after the decimal, which equates to 5. If we look at the scientific notation here, the same exact thing is true. We would have the 1 digit plus the 2 digits, the 2 zeros past the decimal. All of these would be significant. This here is no different than these leading zeros here or trailing zeros. Those are insignificant. Only these are the significant value. So let's do a couple of examples of counting sig figs using the rules that we just talked about. So if we look at this first example, we have 0.036653. We know that these preceding zeros are not counted, so we would actually just count these 5 digits, which would tell us we have 5 sig figs in this first number. The second number is a little bit difficult because we know that trailing zeros like this are only significant if they are after a decimal, but there's no decimal here. So this is really ambiguous. This is what you don't want to do as a scientist because it requires that the person interpreting this value either assumes all 5 of these are significant, or maybe the first 4 are significant, or maybe only the first 3 are significant. And so we can't really assign. We could say that there are 3 sig figs for sure here, but we don't know about the latter 2. So a better way to write this would be 7.2100 times 10 to the 5th. This unambiguously states that all 5 of these digits are significant. And what about analog measurements, which happens a lot in chemistry? So an analog measurement is one where you are interpreting from a measurement scale what the numerical value for that quantity of measurement is. And so often in chemistry, we're using calibrated glassware like this, where these gradations mark, say, the volume of some liquid that you're trying to measure or dispense. So the general rule of thumb here in any sort of analog measurement is start by writing out the digits that we know for certain. Okay, so we can see that the volume is increasing in this direction. We have 3, 4, and 5, and maybe we'll just say that this is in milliliters. That's a common volume measurement in chemistry. And what we know for sure is this line here marks 4, and this line here marks 5. And we can say that this line, or these small gradations in between, must mark 1/10 of a milliliter. So this would be 4.1, 4.2, 4.3, 4, 4.5. So we know for sure there's at least 4.5 milliliters of some liquid in this measurement device. But we also, optically, with our eyes, we can make some assertion based on where the bottom of this curvature of the liquid, we call this thing the meniscus. we measure from the bottom of that meniscus, and where that meniscus crosses in between these gradations, we can actually make a best guess for what this last third digit might be. And so I would venture to guess that this would be somewhere around 4.58. So when we're talking about significant figures, which of these three is significant? Well, it turns out all three of them. All three of these values are significant. This last digit here, this 8, because I had a guess, this is the least significant, but we still mark it as significant because it's not a random number. I was able to assess based on where that meniscus landed in between these gradations that it was closer to 4.58 than it was 4.51. So it's less significant than the first two digits, but we categorize this as three significant digits. And this general process is going to be the case for any time you conduct an analog measurement. Usually, you can make some assessment with confidence for the first two or three digits, and then you'll always estimate the last digit based on how close it is to the last two gradations there. So three significant figures for that analog measurement. Okay, so that brings me to the final point here, which is oftentimes we don't make a single measurement and report a value. More often than not, we measure multiple values and we do some math or arithmetic to produce a new quantity that we want to report. But the real question then is, if we know our two or three measurements that are going to go into some mathematical operation, if we know those to different degrees of significant figures, how do we do the arithmetic? And how well do we know the final computed answer? Right? So your calculator is going to produce an infinite number of significant figures, but it's up to you as the scientist to only report those that you actually know, the actual significant figures. How do you know how many to actually report? Well, it depends on the type of mathematical operation you want to conduct. So let's say you want to compute the gas mileage of your vehicle. To do that, you would measure how many miles you traveled, which would be done with your odometer. So let's say that's 278 miles. And then you'd also have to measure the volume of the gasoline that you used or you combusted to travel that distance. And so the mathematical operation here would be division. So in this first measurement, we know that to 3 sig figs based on whatever tool we use to measure that distance, the odometer. We know 3 of those digits. We don't know anything beyond that. But the volume that's noted in green, we actually know that to 4 significant figures, right? And so the question is, once we do this mathematical operation, we take 278 divided by 11.70, how well do we know this answer? Well, the basic premise here is actually pretty simple to understand. It's impossible for us to do a computation like this and know the new answer any more confidently than we knew any one of the inputs. So if our input here was limited to 3 significant figures, we could never know this outcome to any more than 3 significant figures. Hopefully that makes some sort of sense. And that's going to always be the case for multiplication or division operations. So you'll always keep the least number of sig figs of any of the input values that you put in. So because we only had 3 sig figs in our distance measurement, we could only have 3 sig figs in our ultimate miles per gallon. Okay, it's slightly different for addition and subtraction operations, which is down here in this second example. So in that case, we have these two inputs here. We have 3.18 and we have 0.01315. And the slight deviation here is that in these two operations, addition and subtraction, we keep the least number of digits past the decimal. So in this first case, 3.18, we have 2 digits past the decimal, even though we actually know 3 significant digits. Only 2 of them are past the decimal. In the second number here, we have 1, 2, 3, 4 digits past the decimal. And coincidentally, this also is 4 sig figs. But this rule states that the number of digits past the decimal, the least number of digits past the decimal, is what we'll preserve in our final computation. And since we only knew this first input value to 2 past the decimal, our final answer, once you add these two together, can also only have 2. So that means this number only has 2 digits past the decimal, but ultimately it has 3 sig figs associated with it in the final answer. These two rules are going to be true for any type of mathematical operation going forward in this class. So we'll have to memorize those right away. Okay, let's do a couple quick examples here. So in this first example, we've got a addition operation. Remember from the previous rule that for addition, we are preserving the least number of digits past the decimal for the input values. So here we have 3 digits past the decimal. Here we have 1, 2, 3, 4, 5 digits past the decimal. We're constrained by this one because we only know it to 3. So that's going to give us a value of 24.612 grams. And down here we have a division operation. That's what's meant by this backslash. So this is 4.6742 grams divided by 0.00371 liters. In this case, we're preserving the least number of sig figs, not the decimal numbers. So we need to count sig figs. We've got 1, 2, 3, 4, 5 sig figs in this first number. So there's 5 there. Remember, these zeros don't count, so we don't count those. So we only have 3 sig figs here. So that means our final answer can have no more than 3 sig figs. We can't know it any more or any more confidently than the least known input value that's going into that computation. So that's going to give us this value of 1259.89. That's keeping too many digits, so let's get these digits to something more reasonable. This is going to require us to round. That'll give us 1260, and probably a less ambiguous way to write this with 3 sig figs, because this has a trailing 0, would be 1.26 times 10 to the third. And that would be in units of grams per liter.